This talk is based on a past and ongoing work with a lot of people. Is Professor Bajaj from Texas, Andrea Micheletti and Podio Guidugli from University of Trento Vergata, and Nicola Pugno from Trento. This is a short outline of my presentation. I will start with a few facts about carbon allotropes. And then shortly I will give an account of a theory of continuum shell, a continuum theory for carbon nanotubes. And then the third point, which is the bulk of my presentation, I will present a discrete mechanical model for 2D carbon allotropes, which is based on second generation reactive Rebo potential. And in particular, three applications I have in mind, and these are these three, to discuss the exact geometry of carbon nanotubes, the role of upper stress in carbon nanotubes, and the softening of bending stiffness in graphene induced by stretching. So, due to its valency, carbon is able to form a lot of allotropes. Some of them are very known since a long time. First is the diamond and the graphite. And some of them are very recently considered like graphene, which is a monolayer sheet of carbon atoms arranged in an hexagonal way, which has very interesting properties from mechanical point of view, but not only. There's also fullerene, which can be considered like a graphene sheet in the shape of a sphere. And carbon nanotubes can be considered like a graphene sheet rolled up to form a cylinder. And there are many ways to roll up this sheet. And here we have a simple lattice of graphene. And if we roll up the sheet, ideally, this is an ideal procedure, around an axis which is orthogonal to this dotted line, we obtain something like that at the end. And this is called zigzag. If we roll up around an axis orthogonal to this dotted line, we obtain something like this, and this is called armchair nanotube. And in the middle, we have a variety of carbon nanotubes called chiral. These two, zigzag and armchair, called achiral. We will see later that these two vectors, A1 and A2, are necessary to determine this chiral vector, and then to have the exact geometry of carbon nanotubes. From the point of view of modeling, there are mainly these two families, atomistic modeling and continuum modeling. The first one, and the main exploited, is the molecular dynamics. There's a huge amount of computation made with molecular dynamics. We need to choose a potential and then perform computations. The other two, Monte Carlo simulation ab initio approaches, don't need the choice of a potential, so they are more sophisticated, related with the previous lecture. So we have quantum effects and etc. The other class are continuum modeling, and sometimes graphene or carbon nanotubes are considered like plate or shells, or with like a beam, because carbon nanotubes are very slender, and then someone considers them like beam. And here we have to be very careful, because it is not possible to take the classical theory of plates and shells and consider them like carbon nanotubes or graphene. So here, in this continuum modeling, we have to be very, very careful. The first thing I want to just sketch is a model of single-wall carbon nanotubes. I here write nanoscopically informed, because it's a shell, so it's a continuum theory, but in some sense has memory of what happens at the nanoscopic scale. Here the target was to describe a macroscopic model of a linearly elastic shell. So here the problem is linearly, not the problem. The choice was to have a linear elastic shell. whose geometrical and constitutive parameters are induced by from available geometrical and constitutive information, and all of them depend on chirality. Just a sketch of the modeling approach. All the information we have comes from molecular mechanics, so at the nanoscopic scale. But we want to build something at the macroscopic scale, the continuum mechanics. In the middle, we put something that we called meta-nanoscopic. Nanoscopic is the same as the previous because the scale is the same, but the meta is because different is the point of view that we have in this step and in this second, because here we gather information from discrete mechanics. The first one, we have to consider the bonding energies we have at the nanoscopic scale. And in this first simple example, we just consider stretching energy and angle variation energy. So what we see is the difference of the length of the carbon bond, and here there is the difference between in the angle between two covalent bonds. And there's these two guys are like microscopic stiffnesses. And we suppose that they are known, fitted to experiments or by ab initio quantum mechanical evaluations. So all we know is these two constants. And with these two constants, we want to build up a continuum theory. The discrete mechanical caricature of our bonds is like that. So we have 3 pin-jointed sticks, pair linked by spiral springs. The springs has a stiffness Ks, and the stick has a stiffness Ka. So it's a simple mechanical, discrete mechanical caricature of the bond. And the first thing is to set equal this stiffness Ka and Ks equal to Kr and K theta respectively. The third point here with the discrete mechanics we have then just two constitutive parameters, Ka and Ks, which are known. Just one geometric parameter, which is the slenderness. Here, rho 0 is the radius, the discrete radius of the carbon nanotubes, and L is the length. But if we want to build up a continuum theory, a shell theory, we need at least an elasticity tensor, more than one geometrical parameter, and we need the thickness, then the ratio between the thickness of the shell and the radius, and the slenderness, the ratio between the radius and the length of the tube. So here the point was, one of the main points was to define what's the thickness of a shell, reproducing the behavior of carbon nanotubes. And our recipe here was quite simple, and we had to solve explicitly, so to find an analytical solution of both continuous and discrete versions of a number of equilibrium problems, like axial, traction, radial pressure, and torsion. A number of these problems sufficient to obtain all of these parameters. And then thickness and radius of the continuum object are depending on the constitutive parameters coming out from discrete mechanics. And then the thickness for us is not a geometrical parameters, but in some sense it's constitutive parameters. And this constitutive, the constitutiveness of this object comes from the nanoscopic scale. And the same thing we can say about the continuum radius, which in principle is different with the discrete radius. In some sense, this is the radius of the real object. This is the radius of the continuum object that we claim best fitting the real object. So in principle, they are different. And in our computation, they are different in some sense. So I don't present here the details, but just a sketch of what we have presented. Proposed, and underline the limitations of this model proposed a couple of years ago. First of all, the linearity, both geometrical and material. The fact that we consider a bonding energy harmonic, this is a limitation, and a lot of peculiar behaviors cannot be captured with all these limitations. For instance, the role of pre-stress that we will discuss later, and for instance, the problem I mentioned before, the bending, the softening of graphene. So we can go on and talk about a discrete mechanical model for carbon allotropes, in particular for graphene and carbon nanotubes. And this is based on second generation potential. And with this, we will discuss the three problems I mentioned before, namely determine the natural geometry of carbon nanotubes, disclose the role of pre-stress, and discuss the softening. So we are still in discrete structures. So we define the natural equilibrium of a discrete structure, like a minimum of a functional. And we have to choose a potential, and this potential will be induced by second generation Brenner potential. This potential depends on a string of order parameter, and we call this string psi. And as we will see later, in graphene and achiral carbon nanotubes, just 3 entry strings are sufficient, of Lagrangian coordinates are sufficient to determine this order parameter string because of the symmetry of the problem. Of course, the equilibria are the stationary point of this functional B, and this stationary condition can be written as this way, like an equilibrium operator acting on a stress mapping. So everything can be, we have to be careful to define this stress mapping in the discrete case, and this is what we will do in a second. Let's come back to the geometry of achiral carbon nanotubes. I mentioned the chiral vector, which is the vector determining the way I ideally roll up my carbon nanotubes, and this is described by the integers n and m, which are the components in the basis given by the vector a1 and vector a2, which are the lattice vectors. What is the nominal radius? It's the radius of the cylinder on which the carbon atoms would be placed after an ideal rolling up operation entailing on energy expenditure. Namely, I'm thinking that there's no change in length of this bond when I rolled up the sheet. And this is what is generally called the radius of the carbon nanotubes. Of course, it depends on the integers n and m, because it depends on how I'm rolling up the graphene. R0 here is the length of the carbon bond. But of course, this is not the real radius of carbon nanotubes. This is something, an ideal picture. And we want to appreciate if there's a difference between the natural equilibrium of carbon nanotubes and this nominal radius. And to do that, we need a more sophisticated kinematics, enriched kinematics with respect to the previous one I proposed before. Then the two things entering the energy was the change in length and the change in angle. But here we need also something else, which is the change in dihedral angle. That is the angle between the normal of the plane spanned by hij and the plane spanned by ijk. And as we'll see, this is fundamental in graphene and in carbon nanotubes. So neglecting this energy is a big problem. Consider now a graphene sheet and the ideal rolling of this sheet. Because of the symmetry, because we are here in a chiral, so I just presented a very simple case. This can be easily extended to more complicated case. We have two kinds of bonds. We call it A and B. A is in direction 1, B is in skewed direction. Two kinds of bond angles, alpha and beta. Alpha is between two B bond and beta is between a A and B bond. And we have 5 types of dihedral angles. Here in this picture, it is not easy to visualize because of the color are not really seen. Here there's some yellow, so it's not, unfortunately, it's not possible to realize these different bonds. But if you consider the bond A1, B1, related to this one, we have 5 types of dihedral angles. So the order parameter substring I mentioned before is in this case given by all these parameters, the bond A, the bond B, the angle alpha, beta, and the 5 dihedral angles entering in the bond. If one considers the armchair case, there are some geometric conditions involving all these angles. So the angle beta, the angle alpha, and phi is the angle performed when we are folding the graphene. This can be easily checked. Because of these conditions, some of these angles can be considered like a function of the other. So, as I mentioned before, just 3 parameters are sufficient to determine the substring of these order parameters for the armchair case. It's the same for the zigzag. I just presented the armchair, it's just different conditions we have to consider. In this way, we can define the natural radius, which is the real radius of carbon nanotubes. And this depends on all those parameters we mentioned before, and also the natural length of the tube. Now we have to go to choose a potential. This potential is the so-called second generation Rebel potential. It looks like this. So there's a part which is an attraction function and a repulsion function. These two depends on the length of the bond, and there's a bond order function depending on the angle and on the dihedral angles. So the dependence of the angles is inside this term here. And then we used this second generation Rebel potential for the first time for this reason, because they put inside the dependence on dihedral angles. If you consider terms of Morse or first generation potential, there's not this contribution of dihedral angle. So because we had in mind our discrete model with this contribution, we choose the right Rebel potential. Of course, inside of this function, there are huge of constants that are to be fitted with experiments or something else, and I don't enter into the details of this function. I just need to underline that they depend on the bond length, on the angle, on the dihedral angles. In this way, we find here are the equilibrium equations written in terms of stress. And here the stress, we call it nanostress, are objects work conjugated with a change in length, and sigma A is stress conjugated with a change in length of the A-type bond. We have 2 stress conjugated with a change in angle, and 5 type of stress work conjugated with the dihedral angle. These simple equations need a constitutive prescription, and we use the second generation Brenner potential. So in this case, this is not linear, and they depend on all parameters previously defined. The solution of this equilibrium equation provides the value of all order parameter. Here we have the solution for the radius difference. Here we plot the radius difference in percentage with respect to the nominal radius. Plotted versus the natural curvature. So there's a difference with respect to the so-called nominal radius. It is not huge, but it arrives up to 7%. And difference there's also in the length of the tube. Of course, we can also determine the bond length difference with respect to the classical assumption, and there's a difference that is not huge also in this case, but it's quite important in some cases. Here A stands for armchair and Z for zigzag cases. The last thing for the computing the natural geometry concerns the angles, which are not this value, which is the one could expect. And the dihedral angles are computed like before in this case. The last thing quite interesting is the role of pre-stress, because we showed that both graphene and carbon nanotubes are pre-stressed structures. If we compute the bond stress tau alpha and tau beta in the natural configuration, they are not zero. Not only the bond angle pre-stress, but there's also dihedral pre-stress. This is in carbon nanotubes. In graphene, dihedral pre-stress, of course, vanishes. So there's just bond angle pre-stress. In this plot, we consider the roll-up energy and show that the dihedral contribution to energy is very large. It arrives up to 50%. While this one, it's a simple plot of the energy versus the squared curvature to show that the expected behavior, the linear behavior with the squared network curvature is real. There are some differences, but is tenable. The last problem I want to consider is the band interaction problem of graphene, and consider this problem for detecting the softening properties of graphene. Here the equilibrium equations are not so different with respect to the previous one, but there's a term, of course, depending of the axial load of the we applied. We have always these geometric conditions between all parameters, and we can define this way the curvature of the graphene, depending of this order parameters string. Consider all these geometric relation and the first three equilibrium equations and write them in this compact form, like a function g equal to 0. This function depends on z, which is the order parameter string, and phi. Phi is the angle due to during the folding. So it depends on z, it depends on k, which is the curvature, and depends on the force I'm applying before to bending. This allows to define implicitly z, the string containing the order parameter and phi, as an implicit function of k and f. And if we pick the last equilibrium equation, we have an expression of the couple per unit length in terms as an implicit function of the curvature and the force. In this way, we can define, well-define the bend stiffness of graphene, like the derivative of this object with respect to the curvature, and provide a softening measure, because if we take the bend stiffness and derive with respect to the force, we obtain a number. If this is positive, we have softening. And this is what happens. We have to little bit manipulate the derivative, because this is we have to derive. We are on a manifold. We have to derive on the manifold. So we have a little bit to go with this derivative, and what we obtain is something that in elasticity we could not expect. That is, if we pre-stress the graphene and then we bend it, we have a softening of the bending stiffness. In elasticity is exactly the opposite. The last thing I show here is the simple case when it's the bending stiffness of graphene, so assume that there's no force applied before, and compute the bending stiffness in the way I defined it before. we can ignore the dihedral contribution, so for instance using a first generation potential, and we obtain this nice expression, that is the bending stiffness is 1/2 of the pre-stress, bond angle pre-stress. So the origin of bending stiffness of graphene is just the pre-stress we computed before. This is in the case if we ignore dihedral contribution. If we consider this dihedral contribution, there's this pre-stress, there's also a term which depends on the stiffness of the dihedral spring. So in the complete version, what matters is the pre-stress and the dihedral stiffness of the spring. This is the correct one, I would say, because if you consider first principle, you obtain a value of the bending stiffness like 1.5. In this way, you obtain 1.4. So it is very important to consider dihedral spring, dihedral contribution in the bending stiffness. So with this, I finish my presentation.